In this example video, we are going to look at the velocity time graph of a rebound scenario. But first, let us define some physical quantities. 2a, define speed and velocity and use this definition to explain why one of these quantities is a scalar and the other is a vector. So this question got two parts. First part, we got to define speed and velocity. Let me label this one as 1. All right. And the second part that you need to do is to explain why one is a scalar and the other one is a vector. All right. So let's go. So let's define a speed and velocity first. Speed is defined as the ratio of distance over time. All right. And what about velocity? Velocity is either the ratio of displacement over time, or even a better explanation would be rate of change of displacement. Okay, so the second part, we need to explain why one of these quantities is a scalar and the other one is a vector. So you can say distance is a scalar quantity, hence speed is scalar. Okay, and repeat the same thing for displacement. So this is like bonus marks lah, to work a bit for it, but it's bonus. So displacement is vector, hence velocity is vector. All right, something like that. So remember, there are two parts. Don't miss out both parts. Okay, let's look at the scenario. A ball is released from rest and falls vertically. Let's look at the graph. Release from rest would be at this point here, okay? And then it falls vertically. So when you drop something, right, it will drop faster and faster. So you can see the velocity is increasing, but it is increasing in the positive direction. Increase all the way until this value. This one looks like 10.8 to me. Okay, so it increases from 0 to 10.8. And since this is positive, I already know that this graph is taking the down direction as positive. Okay, the ball hits the ground and rebounds vertically as shown in the graph. Do you know where it hits the ground? It's fall faster and faster, faster and faster until this point. Yeah, CV increase until bloop, this point. So this exact point, this 10.8, where the acceleration or the graph is rudely interrupted by the ground. Isn't that how you feel like when you wake up? Rudely, you were just nicely sleeping, rudely interrupted by the ground. So here is where you hit the ground, or rather touches the ground. All right. Okay, then what happens after this point, after this 1.1 second? Is it 1.1? Yeah, 1.1 second. After this point, it took 0.1 second to rebound. I zoom in so you can see. This one here, it will slow down and stop very quickly. I'm going to change my thickness here. So here is where the ball will stop. But it is still touching. It's still touching the ground because it took 0.5 seconds to decelerate. And then after that, the velocity of the ball increases in the opposite direction. So here, this one will slow down and stop. And then it will increase in the opposite direction, meaning your ball is now going up. Okay, so everything up here, the ball is moving down. Then everything down here, the ball is moving up, just to challenge and confuse you. But this point is where the ball leaves the ground. So when it leaves the ground, the ball will be in free fall once again. That's why this line is parallel to the other line, free fall. Okay, it's only at this rebound time that is very short that the ball quickly U-turn due to the large force exerted by the ground. What does the question want from us? Let's see. Okay, it says here, air resistance is negligible. So obviously, because the graph is a straight line, look at the graph behind my head. Okay, so use the graph to determine the variation, to describe the variation with time t of the velocity of the ball from 0 to 2.1 second. So when we use describe, right, describe V, we want to describe V, we will use words like increase, okay, decrease, or constant. Okay, and also we should also mention the rate. Okay, so is it increasing at a increasing or decreasing or constant rate? So your statement should have both. All right, so let's do part by part. Okay, we can start with 0 time t equals 0 and extend all the way up here. Okay, so we want to stop at where? 2.1. 2.1 is here. This point here is 2.1. Stop here. Okay, let's talk about the yellow portion. All right, so if you want to help your brain, you can start with t. Okay, so write the time. From t equal to 0 second, lowercase t, equal to 0 second, to t is equal to 1.1 second. So I'm talking about the yellow line. Okay, the velocity increases at a, what rate is this? It's a straight line, right? So constant rate. All right. Then the second point. Let's move to the rebound portion of the graph. This part here. Okay, so at first the velocity will decrease until 0 and increase in the opposite direction. Okay, so I will say something along the lines where when t is equal to 1.1 second to t is equal to 2.2 second, 1.2 second. Is it? Yep. The velocity decreases, still at a constant rate because it's a straight line, and increases in the opposite direction. The ball is leaving the ground already at a constant rate, straight line. So in other words, you can say the ball rebounds. Okay, haven't finished yet. Haven't finished yet. We are not at 2.1 second yet. 2.1 second behind my head here. Here this 2.1 second. Teacher, the 2.1 second must come the same leh. Correct lor. Here to here. Okay, so here to here the velocity increases. Okay, decreases at a constant rate until 0 at 2.1 second. So we can continue the story and say for t is equal to 1.2 to 2.1 second. The velocity decreases at a constant rate until 0 or until stationary. So it stops at 2.1 second. So these are all your points because you are describing different portions of the graph. Let me highlight for you so it's easy to see. So what are the marks or the keywords that they are looking for? Okay, so the first mark they are looking for velocity increase at a constant rate, or you can also write something along the lines where velocity increase must have velocity increases or constant acceleration. This is your 1 mark, but you have to mention the time. So until t is equal to 1.1 second, until, or if you say from t equal to 0 to t equal to 1.1, the timing is needed. Timing plus description. Okay, so this is 1 mark, B1, meaning if I see something like, until 1.1 second or from beginning to 1.1 second, the velocity increase at constant rate, or constant acceleration, you get 1 mark. Okay. Second mark is when you mention change direction. So like for example, opposite direction or change direction, or if you mention rebound. Basically, you know their rebound. This is 1 mark. But I give a more complete explanation. Velocity decrease and then increase as a good habit. So always talk about whether the magnitude increase or decrease. The first line is magnitude, which is value. And then you can use this as a guide lah. Increase or decrease. You look at magnitude and then talk about the rate. Okay, which means you need to look at the gradient. Rate here, we look at gradient. Okay, the last mark you will get if you say velocity decreases, okay, at the constant rate until stationary, and I missed out something, constant rate, same as the initial acceleration. Okay, because these two lines, the yellow line and the blue line, they are parallel. Okay, so decreases at a constant rate, same as the initial acceleration until stationary. This is B1. So a lot of details is needed to answer this kind of question. So it's good to take your time and then be as thorough as possible. If let's say there is relative values that you can compare, for example, the final acceleration is equal to the initial acceleration, you should also include them. All right? But yeah, that's it. Velocity decreases to 0 or decelerates to 0 at constant deceleration, same as the initial acceleration, because they are both gravity. This is G, this is also G, the gradient. 9.81. All right, that's it. We can now move on to part 2. Part 2. Calculate the acceleration of the ball after it rebounds from the ground. Show your working. Okay. After it rebounds from the ground. So we establish from the graph, right? Okay, I'm going to bring the graph here so it's easy to see. We've established from the graph that we will come into contact with the ground here, and then we will leave the ground here. Okay. So here is where you hit the ground. And then here is where you leave the ground. Hit and run. Hit and leave. Okay. So we are looking for the acceleration after the rebound. So then I can tell just from this graph that the acceleration after the rebound, this one is t is equal to 1.2 onwards. So I tell you what, I will take this coordinate. Let me zoom in a bit so we can write down the coordinates. I'm going to take this coordinate here. Change pencil. So this one, this coordinate is, you look at here, this one is negative 8.8. And this one here is 1.2. So I will take 1.2 comma negative 8.8. Okay. You want to find gradient, you need 2 points. Let's look for another point. Maybe teacher, you can use this one. Yeah, no. The low-hanging fruit is this one. So this will be 2.1 comma 0. So I want to find the gradient of this line. Of course, you're like, teacher, can I, this is straight line, or can I take this point? Can. Any point also can. All right. But if you want to do the right thing, so to speak, you should take this point, because the bigger, the further away the plots, the more accurate the results will be. But this is a very beautiful line, so I think you will get the same result. But let me just put this in. This one here would be 3.0 comma, this is still 2 boxes here, 8.8. I think I will use 3.0, 8.8, and 1.2, negative 8.8. Okay, so I will use both coordinates to find my gradient. Let's go. Gradient acceleration is equal to gradient. Please announce this early to get your insurance mark. Okay. Announce early to get your insurance mark. So after rebound is between 1.2 second to 3.0 second. And I decided to use both coordinates, but I need to find the gradient. So if I announce early that I'm saying that acceleration is gradient, I should immediately get a method mark in case you calculate wrongly. Take insurance first. Right? So the two coordinates that I will use, I'm going to write out the coordinates now for you. Coordinates that I used was 1.2, comma, negative 8.8. You can always check the graph again. And then the second coordinate I use is 3.0, comma, 8.8. Okay, so I will take y1 minus y2 divided by x1 3.0 minus x2 1.2. So if I press my calculator, that would give me, press with me now. Don't let me press alone. Very sad like that. Okay, 9.78, 7777777, okay, 78 lah. 9.78 meter per second. You want to put 9.8 also can. All right, your answer should be 2 to 3 SF. I'm reasonably satisfied. Okay, so in this case, you may be wondering where the marks are. If you write A is equal to gradient, you already get 1 mark. Even if everything else is wrong, you log in that mark first lah. Okay, then you choose any appropriate coordinate. If you don't want to write out the coordinate like me, also can. All right, you can just substitute inside. I can double check the coordinates. This will be C1. Okay, leading to the final answer of 9.8. This is A1. Okay. All right, part 3. Calculate for the ball from 0 to 2.1 second, the distance moved and the displacement from the initial position. Okay, let us go and peek at the graph again, okay? We want to find 0 to 2.1, which is from here all the way to here, okay? What is the distance moved and what is the displacement from the initial position? Okay, one by one. Let's say I want to find this area. Okay, so this triangle here. Because we know distance and displacement, all this is related to area. So let's say I look at this blue area. Okay, so I have shaded the graph and you can see the blue color portion is when the ball is being released. So this part is when it's traveling down. Okay, and then after that, it hits the floor, it leaves the floor, and then this is when it's traveling up. Okay, you may be thinking, teacher, you zoom in you see this part here, this little bit extra. Let me try and see. This one is like testing my fine motor skill. This yellow part here, teacher, no need to count. No need. This is when the ball is being squished. Okay, so whenever the ball hits the ground, it will be compressed. That little bit of compression is represented by this tiny slice of area that has nothing to do with the displacement. Okay, so later on, when we move on to the next chapter where we talk about collisions, you can look up slow motion videos of collision. When the ball hits the floor, it will compress. So this little yellow part is the distortion of the ball that we will ignore. Don't count. Okay, so we're going to take the triangle. So we have two triangles. We have the blue one where it is moving downwards. I'm just going to sketch out the triangle here for us. So here would be, remember, I'm only taking the blue color side. So the yellow part is not there. This is 1.1. So this is 1.1. And this side here, if you recall, this is 10.8. Yes, 10.8. Okay, this is the blue triangle. And the other triangle, when it's traveling down, the purple triangle, this is 1.2 all the way to 2.1. So this is 0.9. Okay, the time is less because you lose kinetic energy, and when you rebound, you will travel through the same distance with less time because you don't have to go so high. All right, so then if I look at the height here, it is negative 8.8. So this side is 8.8. This is when it's moving up. This is when it's moving down. Okay, so with the dimensions in place, now I can find both distance and displacement travel. So distance move, let's say I call this D, is equal to the distance when it travels up plus the distance when it's traveling down. So this value here would be half times 1.1 times 10.8 plus half times 0.9 times 8.8. Because later I need to find displacement, right? I'm going to calculate these two numbers separately. So half times 1.1 times 10.8, this one will be 5.94. Okay, and this one here would be times 0.9 times 8.8. This will be 3.96. So if I add them together, I would get 9.9 meters. So I go up, basically the ball fall 5.94 meter, moving down. And then after it collides with the ground, it will go up by 3.96 meter. Okay, so if you want to find the displacement from the initial position, displacement you have to minus because the ball is going to end up here at 2.1 second. So we will minus here to here is your S. So to find S, I will take 5.94 minus 3.96, the difference in area. And that would give me 1.98. Teacher, can I write 2.0? Can. Up to you. Okay, but I write 1.98 lah. So this one is like a lot of marks. Yes, sometimes they are quite generous when it comes to graphing. So if you find the first area correctly, and you take the two area and you add them together, you get 1 mark. Okay, so if you have any indication of adding the area, you get 1 mark. You substitute the answer is another mark. So the first mark is when you take area plus area. Okay, the correct area lah. Second mark is the substitution. All right, and the third mark is the final answer. Okay, mark your own work when you do questions so you know what the mark scheme wants. Okay, second mark is when you subtract the two values, you get 1 mark. This is C1. You show the subtraction, and then your final answer is A1. Okay, so this is the calculation portion where we use the gradient to find the acceleration and the area to find distance and displacement. Okay, the next part. Sketch the variation of the speed time graph. Okay, so I conveniently brought the velocity time graph along with me. Okay, so I want to draw the speed time graph. So speed, if you think about it, right, speed and velocity is related. Speed is actually the magnitude of velocity. Let me write here. This one is the magnitude of v. So if this is the magnitude of velocity, then you look at this graph or you can copy paste over. Okay, so this is what I'll do. I am going to copy the graph almost identical. Okay, maybe I use a thicker pen. Okay, so, and I should use straight lines. So when you're drawing this in the exam, please use straight lines, okay? So I'll take the magnitude, whether it's positive or negative. So this one is 10.8, and then this one here is 0. Okay. So then I'll move this over here. So from 0 to 10.8 here to here. Let me see, 10.8 is here. This one is 0. Copy only. Marks for copying the graph. Yes. Okay. What about the next portion? The next portion from here decrease to here when the rebound time will have the same shape. But you see, we need to modulus the graph because it's magnitude only. So let me draw out the same graph first, but I'm going to draw it all the way to 8.8 here. At least I'll try to draw it here. Okay, so the negative portion have to be flipped. Okay, negative portion, I'm going to flip this. Okay, so you will, generally speaking, modulus the graph. All right, let me try to do that. Okay, so once you flip the graph, this side here should be 8.8. Let me try to make that happen. 8.8. Okay, so the graph will look like it has gone through a modulus or a reflection on the x-axis lah. So it's going to be looking something like this. Okay, we'll pass through 1.2, 8.8. This point here, 8.8, is moved. This part is flipped over. What about this part? This section after it leaves the floor. If you're thinking about here, this is negative, we also will reflect. So what I will do is I will join the line from here, and I know that it will reach maximum height at 2.1. So let me put this side by side so you can see it's going to reach here at 2.1. So 2.1 is here. So basically we're just performing a reflection here. So whatever that was the negative direction, we flip up to the positive side. Okay, so I'm going to draw a line for that. Just draw a thin line so that it's a bit more accurate. So in the exam, you should use a ruler, okay? I'm going to use a line tool to do this here. So the triangle, basically the bottom triangle, I draw modulus lah. I get this one. Then the rest I can just copy as usual. So this part is already positive. I will continue the graph from 2.1 to 3.0. Okay, let's do this. 2.1 is 0 meter per second. And then 3.0, we managed to reach back the same height, or sorry, the same speed, because the ball is falling down. All right, so something like this. Okay, let me zoom out so you can compare the graphs. So essentially what I have done, okay, let me make them comparable sizes. Essentially what I have done is I have drawn the modulus of this graph, which is what magnitude represents. So in the exam, what you need to do is you just need to find this coordinate down here. You find this coordinate, and then you plot here, and then you join the lines. Okay, of course, you need to find all the important coordinates. Now, all of these have to be there. All right. So to get the 2 marks, it has to be the correct shape, and then all the graph is positive. So let me show you the mark scheme. So they are trying to test whether the candidates understand the idea of vector and scalar. So if you know that speed is a scalar, we define this in part A, you will draw something that is always positive, always above the time axis. All below is a bit weird lah. Okay, so I think all above the time axis is fair. Okay, correct times for 0 speed. Okay, so this means at 0, 1.15 and 2.1. Now, the correct times are here. 0, 1.15 right in the middle, 2.1. Because these are the places where we intersect or we cut the time axis. So important points have to be there. And the peak speed is also correct, meaning this is this and this is all correct at the right time. So we check all the extreme values. So when you draw a graph, especially if a scale is driven and you're not given and you're not sketching, make sure whatever important values that you have calculated and collected since the first part of the question is all input inside the graph. Okay? Right. So that's it for this rebound question. It is also a vector and scalar question in disguise, testing you to see whether you understand the idea of magnitude. They also ask you to look at the gradient and the area and describe the graph. It's a very thorough question. Okay, so make sure you try more questions to make sure that you don't accidentally lose mark because of lack of attention to detail. All right, and I'll see you in the next video. Take care. Goodbye now.